So good afternoon, everybody. The ABC of stellar evolution, perhaps not your typical Geological Society talk. I'm looking at the birth, the life and the death of stars, and the reason this might be of interest to you is because along the way we're going to see the origin of the elements in the periodic table beyond hydrogen and helium, which of course explains the elements as they exist on Earth. So I'm looking at birth, life and death of stars. With birth, we're looking at nuclear fusion. We're not going to be spending our time thinking about nuclear physics. We'll just touch upon what's going on, and we'll think about how stars come to be. We'll be thinking about how stars live, and all stars are a balance between gravity and radiation, and we'll see why that's important. We'll think about how different stars lead different lives. And perhaps the most relevant part of this talk for you is we'll see how, when the fuel runs out inside a star, it gives rise to the birth of new elements. How do stars die? Well, they might die with a bang and they might die with a whimper. And we'll think about what's left over once a star comes to the end of its life. One possibility is the enigmatic black hole. So let's just remind ourselves where we are with respect to the sun's life. If we think about a timeline starting at 0, which is the Big Bang, where everything came to be, the Big Bang generated a very large amount of hydrogen. I am not going to talk in any detail about what the Big Bang was and how it generated all that hydrogen. That's the subject of a completely different talk. So we're simply going to assume that the Big Bang generated shed loads of hydrogen, and then the sun started using that hydrogen. We are now at 13.8 billion years after the Big Bang, and the sun condensed from a large hydrogen cloud about 4.5 billion years ago. And the sun is now roughly middle-aged, in the sense that now we are 4.5 billion years into its life, and it's probably got a similar amount ahead, perhaps 5, maybe a little more billion years, before the sun comes to the end of its life and starts to change. It will start to expand, its outer atmosphere will expand into a red giant, and I'll be saying a little more about this in the slides to come. And that outer atmosphere is probably going to get blown away and leave a small core, which is a white dwarf, which is how the sun is going to end its life. So bear in mind these little circles there are purely schematic. I'm not trying to show the genuine size of the sun, the red giant phase and the white dwarf phase. I'm just trying to put it in some sort of perspective, reminding you that the sun is in the middle of a very stable part of its life, but towards the end of its life it's going to change rather dramatically. So what's going on at the heart of a star? So at the core of a star, the pressure and the temperature, the conditions are just right to fuse hydrogen into helium. So what's going on is we're taking hydrogen nuclei, protons, and they are being fused into helium. So you can see, we're not going to talk about the details, but you can see the end result is if we start with 4 nuclei of hydrogen, 4 protons on the left, we end up with 1 nucleus of a helium atom, which happens to be 2 protons and 2 neutrons. We're not going to worry about the detail of why 2 protons turn into 2 neutrons. All that matters is for every second of the sun's life, 600 million tons of hydrogen are being converted into 596 million tons of helium. So clearly there's a small discrepancy there, but bear in mind that the sun fusing hydrogen into helium to release energy doesn't actually use up much of its fuel, in the sense of that many million tons or that many kilograms being converted. There's still roughly the same amount of mass at the end of the day after we've done this fusion. The actual loss is actually quite small because it's such an efficient process to take matter and convert it into energy through this fusion process. So stars are not just nature's way of lighting up the universe, they are fusion factories, if you want to think of them that way. They are the factories that make the elements heavier than hydrogen. So the Big Bang was very effective at producing shed loads of hydrogen, and stars are the way of converting the hydrogen into everything else in the periodic table, effectively. So yes, it is a very good question, where does the hydrogen come from, but it's not going to be covered in this particular talk. Okay. So where do stars come from? In fact, anybody can make a star. It's actually quite easy. You only need to do 5 things to make a star. Number 1, start with a very big cloud of hydrogen. And number 2, you wait. And number 3, you wait a little more, and then you wait a bit longer, and then you have a star. In other words, to make a star, all you need is a large amount of hydrogen and a certain amount of patience, and you just let it do its own stuff. You just let gravity take effect. And as long as you start with a big enough cloud of hydrogen, you will end up with a star if you wait a few million years. So in that sense, it's not difficult. It's, you could argue, inevitable. After the Big Bang, if you wait long enough, you will get stars. And if we look out into our galaxy, we see huge clouds of hydrogen, which are effectively stellar nurseries. This is the nebula in Orion, the Great Nebula in Orion. It's a particularly large one. Actually, it's particularly close as well, so it looks quite large in our skies. But there are huge numbers of these hydrogen clouds around the galaxy. And right in the core there and elsewhere, stars are being born in a manner that we'll see in just a moment. So what is it that triggers star formation? If we have so-called giant molecular clouds floating around the galaxy, why do we call them giant molecular clouds? Well, for 3 very good reasons. 1, they look like clouds, as we perhaps saw in the last picture. They consist mainly of hydrogen molecules, and yes, you've guessed the 3rd one, they are big. Typically not just a few light years across, which is the typical distance between stars when we look out into our galaxy. These giant molecular clouds can be tens or hundreds of light years across. So what makes a giant molecular cloud collapse? There are a number of possible triggers. One trigger is one cloud that happens to drift and pass through another, and the gas in one cloud effectively collides with the individual atoms in the other cloud. It is also possible that the death of one star, which might explode as a supernova, can actually produce shock waves that go rippling through a cloud, and that rippling effect through the cloud can actually trigger star formation. In other words, the death of one star might actually trigger the birth of a whole host of new stars. And a third trigger might be the collisions of galaxies, which sounds extremely violent, but you could argue it's actually the first point all over again, because when 2 galaxies collide with each other, it isn't the stars that go crashing into each other. The stars actually probably miss each other as 2 galaxies pass through each other, but it's the gas clouds that collide with each other and again trigger new star formation. So when we look at galaxies, we can see where the star formation is taking place because hydrogen clouds tend to glow with a slight pink colour, and so in this particular picture all of these little knots that show up as pink are little regions of stellar formation. These are star forming regions within the galaxies, and in a galaxy with spiral arms they tend to be dotted along the spiral arms. Here we see a face-on spiral galaxy which has a small neighbour, and this neighbouring galaxy appears to be interacting with the principal galaxy that we can see. And whenever we have 2 galaxies that are either interacting or perhaps colliding with each other, we get a little bit of a tug of war. We get tidal effects of gravity from one affecting the other, and hence we get a lot of this pink here. We get a lot of star forming regions in this galaxy, probably because of this neighbour on the right hand side. And there are some galaxies that we see which are quite definitely colliding. We see this particular pair of galaxies in which there are huge tails produced by the tidal forces as these 2 galaxies have become close to each other. If we look in a little more detail with the Hubble Space Telescope, we can see that region in the red rectangle more clearly, and again we see huge regions of pink as well as the 2 galaxies and a lot of this brownish dust in between. We see an awful lot of pink, indicating that the collision of these 2 galaxies has triggered a great deal of star formation. We can see that in a very crude simulation here when 2 galaxies collide with each other. I remind you that the stars themselves are not actually crashing into each other. The two galaxies virtually pass through each other without any stars hitting each other, but the tidal effects, the tidal gravity forces between the two, disrupt the structures of both galaxies and can actually produce a huge amount of new star formation in the gas clouds within both of the galaxies. So let's have a think about how star formation works. This might look like a star, but in fact this is just a large spherical ball of gas. This particular simulation, carried out by Matthew Bate and his co-workers at the University of Exeter, they've done a simulation in which they start with a very large ball of gas, hydrogen. It's perhaps a few hundred light years across. And it's not totally uniform, because in order to get a more realistic collapse of a large cloud, they've actually given each little part of the cloud a slightly different density and perhaps a slightly different velocity. So they're not all static. Each of the little parts of this cloud are moving in random directions with random velocities and random variations in a slight density variation across the cloud. And then the computer simulation can simply be told, right, let gravity do its work. What do we see as this star cloud collapses? So let's run the simulation. So we see that some parts of the cloud happen to be moving off in one direction, but most of the cloud appears to be collapsing, and the density and the temperatures are increasing, indicated by the more yellow regions of this particular cloud. Let's zoom in a bit so we can see what's going on. When the density is high enough and the temperatures and the pressures within the cloud are high enough, it can ignite the nuclear fusion process. When the protons of hydrogen are forced close enough together to fuse into helium, then a star is born. And we can see this popcorn effect of lots of these stars being born. They are born with essentially a range of different velocities. Some are moving only a small amount and stay fairly close. Some stars are moving fast enough that they get thrown away completely from what ultimately will be this cluster of stars that is being born out of this large cloud. So you can see it's like bees in a beehive here. We're generating thousands of stars out of this huge cloud of gas. If we back off a little bit and do a little spin so we can see what it's like, we can see that a lot of the gas has been used up, and the gas cloud ends up with a rather irregular looking shape, and we've generated perhaps thousands of stars, a lot of which are still clustered close to the centre of the cloud, and some have been lost. If our sun was made this way, it is thought that our sun was actually thrown out of the star cluster that it might have been born in, and we have no idea which particular cluster that might be. We can't trace its roots, if you like, back to its birth cluster. So if this is what simulations show us, then is that in any way related to what we actually see? If we ignore the red cloud for the moment and just think about all of the white dots that were generated in this star cluster, does that look like the sort of star clusters we see when we look through telescopes into our galaxy? Well, yes, it does pretty much. So we think we've got a pretty good idea of how stars come to be in terms of collapsing from hydrogen clouds and producing the sort of clusters and individual stars that we see in the galaxy. When it comes to understanding how stars work, there's only a few limited number of fundamental things that we need to think about. And one of the principal ideas of how stars work is based on this idea of balance. Gravity, of course, is trying to crush the star, but that's being balanced by the fact that at the core of the star we have this fusion engine. We are fusing elements, and that's producing radiation, and that radiation produces an outward force which balances gravity. Gravity trying to compress, radiation trying to expand. And stars are always a balance between gravity and radiation. If those opposing forces are equal and opposite, then the star is stable. But if, for any reason, gravity and radiation get out of balance, then the star must evolve. It must change. And many aspects of how stars are born, how they live, and how they die can be explained in terms of this balance and what I like to think of as the ABC of stellar evolution. There's only these three things that you need to get your head around to understand how stars behave. So one is, we've already mentioned that if we want to fuse, for instance, two protons, which are the nuclei of hydrogen atoms, if we want to fuse them together, that's a little bit of a problem. We have to get to high temperatures and high pressures simply because they are charged. The nuclei, or protons, are positively charged, and so they repel each other. So if we want to get them close enough that they are going to fuse together into helium, we have to get them moving quite fast, i.e. high temperature, and we have to get a lot of them in a small volume, i.e. a high pressure. And only then can we actually get the nuclei to fuse. And that's true whether we're dealing with hydrogen, trying to fuse them into helium, or whether these represent two helium nuclei, which are also positively charged and again are repelling each other. So again, we need high temperature and high pressure to get them close enough to accelerate the fusion process. So if we get things hot, we accelerate fusion. That's the A of the ABC. We already know what the B is. If a star is in equilibrium, then the forces are in balance. And if it ever gets out of balance, it must change. The third thing we need to know about stars is that compression produces heat. We know that from trying to inflate a bicycle tyre, for instance. We put the air in, we compress the air and the bicycle pump get hot, and we know that, and stars in a sense are no different. It's essentially the same physics. It's on a somewhat different scale, but when you compress a star, you increase the temperature of the core of the star. So there's the ABC, and pretty much everything we need are built in to the ABC. Let's just have a quick look at where stars are if we decide to classify them according to their temperature, which is the horizontal scale. It's rather odd in the sense that it always goes backwards. The colder stars with a surface temperature of a few thousand Kelvin are on the right, and as we go up in temperature, the stars go to the left. 10,000 in the middle, 30,000 Kelvin. Remember, this is the surface temperature. It's not the temperature in the core where the fusion is taking place. It's the surface temperature. So we have red stars on the right and blue stars on the left, simply because of their surface temperature. And they are plotted also on the vertical scale according to their luminosity. And for convenience, we're taking the luminosity relative to the luminosity of the sun, simply because the sun is not particularly dim or particularly bright, and it's in the middle there. So there's our sun plotted, and by definition, it's 1 on the vertical scale because its luminosity is equal to the luminosity of the sun. And on the horizontal scale, the sun's surface temperature is a little less than 6,000 Kelvin, which is why it emits mainly in the visible part of the spectrum, which of course is no coincidence. So dimmer stars would have a lower surface temperature, perhaps down to as low as 3,000 Kelvin, and the hot blue stars will have much higher temperatures over on the left-hand side. So we'll be thinking about the top right-hand corner and the bottom left-hand corner when we think about how stars evolve. All we have to know for this is that a lot of stars sit on this little diagonal bit of the classification scheme here, the so-called main sequence. Stars that are sitting in this region are stable for a length of time which we'll see depends on what the mass of the star is. But at the end of the star's life, a star will move off the main sequence. We'll see that shortly. So, stars of different mass will follow quite different lives. If we have a high mass star, and again I'm talking about relative to the sun, just for convenience, stars that are much more massive than our sun, they have a great deal of fuel. So you might think, well, surely if a star has got a huge mass, it's got a huge amount of fuel, so surely it will last a long time. That fuel will last a long time. But in fact, because it's high mass, the gravitational forces are very strong in high mass stars. And so to maintain balance, you need a huge amount of radiation generated in the core. And even though you're starting with a lot of fuel, because you need to burn that fuel so fast to maintain the radiation against the pull of gravity, the nuclear fuel must be used at a prodigious rate in order to keep the star in balance. So in fact, high mass stars don't live very long. Instead of living for billions of stars, such as our sun, A high mass star might live for only millions of years. And as you appreciate as geologists, a few million years is not enough to form the sort of planets that we would expect and form life on those planets if we only had a few million years to play with before the star came to the end of its life. So live fast, die young. That's the mantra for a high mass star. And the opposite, of course, is true. If we start with a low mass star, you might think they don't have much fuel, so they don't last very long, but because the gravitational forces are relatively weak in a low mass star, let's say much lower mass than our Sun, so the radiation forces do not have to be very high in order to keep the star in balance. So although it doesn't have that much fuel, the fuel does in fact last for a very long time because gravity is not so strong because of the low mass. If the star is, let's say for the sake of argument, 1/10 of the mass of our Sun, we're not even sure how long the stars might last. Theoretically, we can calculate how long they might live for, but if stars live for more than 13.8 billion years, which is the lifetime of the universe so far, if they're predicted to last for 100 billion years, well, we haven't seen any stars of that mass die yet, because the universe is only so old, and we would have to wait much, much, much longer to see these low-mass stars eventually die. So theoretically, we've got an idea of how they behave, but we haven't actually seen it happen yet. Let's just take a very brief aside, just because I think this is quite interesting. But we've said that mass can vary. In fact, it might vary from some low mass stars, might be perhaps 100 times lower mass than our Sun, and a really massive star could be perhaps 100 times more massive than our Sun. So it doesn't range by that much, 100 times less or 100 times more. But in terms of size, the variation can be much more extreme. And just as a little aside, let's think about how that can vary. If we start with the planets, you're probably familiar with the one on the right there. If we just order them not in the standard way of distance from the Sun, let's order them in terms of their size. Mercury the smallest, then we have Earth, and if we have a second pane here, there's Earth. We clearly have a different scale on this particular panel. There's Earth in the bottom left, and then we have the ice giants and then the gas giants. So this is a reminder that Jupiter is some 10 times larger than the Earth in terms of its diameter. Let's do that same trick again. Let's take Jupiter and shrink that down to the bottom left of the next panel. So there's Jupiter in the bottom left, and we see that one of the smallest stars, in this case Wolf 359, is not that much bigger than Jupiter, which is why occasionally Jupiter is referred to as it's a little bit like a failed star, in the sense that if Jupiter was much more massive and a little bit bigger, it could actually undergo thermonuclear fusion at its core. So the smallest stars, not much bigger than Jupiter. Then there's our Sun, and then there's the star Sirius. Sirius is a bright star in the winter sky. It's not particularly large, it just happens to be bright because it's actually quite close to us. Let's do the same trick again. Let's take Sirius, let's shrink it down to the start of the next panel. There's tiny Sirius, and now we're seeing these huge stars, these red giants. They do indeed look a little more orangey, and of course they are absolutely vast compared to the size of Sirius, which remember is a little bit bigger than our Sun. So you can see these red giants can be not just 10 times bigger, but even more than 10 times bigger than our Sun. But that's not the end of the story. Let's take Aldebaran, shrink it down for the next panel. There's Aldebaran in the bottom left, and then we have Rigel, Antares, Betelgeuse. You can see that Antares and Betelgeuse are absolutely huge. They are supergiants, even compared to Aldebaran, which could be considered to be a large star. These stars, like Antares and Betelgeuse, are absolutely vast. Remember, the mass is not necessarily huge. The mass could be anything from 100 times less to 100 times greater. Even if Betelgeuse was 100 times the mass of our Sun, you can see that here, with this huge volume, it simply means that the densities must be very much lower. And it's almost the end of the story, because if we take Betelgeuse and put it down in the bottom left and then look at the largest stars we can find, this perhaps is slightly out of date now. The largest one I could find a little while ago was a star called VY Canis Majoris. Not a great name, but there we are. I'm sure that they have now found stars which are slightly bigger than that, but not by a huge amount. There could be stars which are perhaps 20 or 30% bigger. But you can see that the largest supergiant stars are absolutely huge compared to the size of our Sun, even though the mass might be a relatively modest 10 or 100 times bigger. The physical size can be vast, assuming the density is relatively low. And just for a little bit of fun, if we actually put the Sun next door to the largest star, VY Canis Majoris, perhaps you can't see VY CMA there. Let's bring it in from the right hand side. There we go. Those are the two stars to the same scale. Actually, it's a little bit of an exaggeration. I haven't exaggerated the size of VY Canis Majoris. I've actually exaggerated the size of the Sun in this particular graphic. If I put the Sun to the correct size, I don't think it would be large enough to actually fill 1 pixel of the screen that you're looking at. So I've made the Sun just a little bit bigger for the point of comparison. So in terms of the volume, you can see the volume differs by enormous amounts, even though the mass doesn't. That's just something to bear in mind. So let's get to the heart of the matter. What happens when the fuel runs out? If our Sun is quite happily fusing hydrogen into helium, it's been doing that for 4.5 billion years, and it's probably going to do it for another 4.5 or 5 or 6 billion years. The question is, what happens when the fuel runs out? So remember that the nuclear fusion, it's sometimes called burning, but of course we don't mean burning in the sense of burning carbon in an oxygen environment. Nuclear burning is just shorthand for nuclear fusion into heavier and heavier nuclei. The fusion process doesn't use up much of the star's mass, as I said earlier. For instance, in every second of the Sun's life, it burns 600 million tons of hydrogen and converts it into something like 596 million tons of helium. And the 4 tons that is lost, that through E equals mc squared, that loss of mass is converted to energy, and that is radiated out from the core. It takes quite a long time to get through the actual various layers of the Sun and then come belting through the universe and actually start warming up the Earth. It might take thousands or hundreds of thousands of years for the radiation in the core to reach the surface, but of course once it's left the Sun, it only takes 8 minutes or so to go the distance of 150 million kilometers from the Sun to the Earth to warm the Earth up. Because only a little bit is lost, even after some 10 billion years of the Sun's lifetime, 99% or more than 99% of the mass of the Sun is still there. It's been converted from one element to another element, but essentially, in terms of how many kilograms are there sitting there, it's effectively the same number. It's just been transmuted from one element into another element. So what happens when the hydrogen runs out, or when we get close to the point at which there's no more hydrogen to fuse into helium? Well, we use the ABC of stellar evolution to tell us what's going to happen. When the hydrogen starts to run out, the radiation being generated in the core is going to start to drop. And remember, because of the balance, if the radiation starts to drop, the star is then going to get out of balance. Gravity is still doing its stuff, but the radiation is dropping, which means gravity now wins over radiation. What happens? The star shrinks, it compresses. What does compression do? Compression generates heat, which means the core gets hotter, which means after a little while the core is hot enough to actually start fusing the next element. In other words, we're no longer fusing hydrogen into helium, or at least we're getting close to no longer fusing hydrogen into helium, but once that fuel starts to run out, the core compresses to the point where it's now got enough temperature to start pushing helium nuclei together. They've got 2 protons in the nucleus, so it's even more difficult to fuse helium compared to hydrogen, hence you need a higher temperature and a higher pressure. But because this imbalance has produced compression, and the compression produces higher temperatures, we can now start fusing helium into heavier elements. So it accelerates the fusion process and we get radiation increasing again. So that's how the ABC works. When the fuel starts to run out, we get out of balance. Because we're out of balance, the star compresses. Compression makes the core hot, which accelerates the fusion process, which will bring the star back into balance again. And in principle, that whole process can repeat, not indefinitely, but when you think eventually, when the helium runs out, what's going to happen? The same thing will happen again. It'll get out of balance, the star might compress to accelerate the fusion of heavier elements and bring the star back into balance once more. It can't go through that loop an indefinite number of times, but in principle, that ABC determines how stars evolve. To see that it doesn't happen indefinitely, we need to see something about nuclear fusion. Again, I'm not going to turn this into a nuclear physics lecture. All we need to worry about is the fact that when we work out how much energy do we get out of nuclear fusion, there's a characteristic shape to the energy we get out as a function of the mass of the elements that we're fusing. And here, the vertical axis effectively tells us how much energy do we get out for every kilogram of fuel that we fuse. In other words, if we fuse hydrogen into helium, so if you like element 1 into element, the mass here of 4, it's the nuclear mass, not the number of protons here. So we have a mass of 1 and a mass of 4. If we fuse hydrogen into helium, this vertical distance between the two tells us how much energy comes from that process of fusing hydrogen into helium. For every kilogram of hydrogen, which generates about a kilogram of helium, we get that much energy out. And if the process were to continue again towards the end of a star's life, if we were to fuse helium into heavier elements, we can pick out a few milestone elements and we can say how much would we get if we took helium nuclei and fused them to make carbon. You notice this curve is starting to bend over, and the amount of energy we get out by burning 1 kilogram or fusing 1 kilogram of helium, notice it's less. Even though we start with the same amount of fuel, the same number of kilograms, the amount of energy we get out is less. In other words, you could say it's less efficient. Fusing hydrogen into helium is very efficient. Fusing helium into carbon is less efficient. And if the process continues again, what if we were to take carbon nuclei and fuse them into heavier elements? When we get to neon, again, the step is less. It is less efficient. We can fuse neon into silicon and we get less again. And you can see something interesting happens when we get to the point where we start fusing silicon into iron. We're at the top of this particular graph. In other words, if we get to iron and then say, well, how much energy are we going to get out if we start taking iron and fusing iron nuclei together? The answer is we don't get any energy out. We're on the downslope beyond iron. So in other words, instead of that's how much energy we get out of the process, a downslope means we have to put energy in if we want to get to heavier elements, such as, for instance, I've just picked at random silver and gold, for instance. So you can see that the idea of fusing elements in a star, describing stars as fusion factories that generate elements, works fine until you get to iron. Iron, if you like, is the most stable nucleus. And iron, when you fuse it into heavier nuclei, does not release energy. You have to force iron to fuse. You have to put energy in. You don't get energy out. So it's not a mechanism by which stars can shine. So something fundamentally is different up to iron and from iron onwards. Let's just think about the consequences of the fact that the efficiency gets lower and lower and lower as you go up. From hydrogen, let's think about a chain of possible nuclei. I'm not talking about every element in the periodic table from hydrogen to iron. I'm just picking out a few milestones, because if you can generate carbon, you will also generate carbon that is radioactively unstable. You'll generate other isotopes, and these will decay and fill in the gaps, if you like. So if we want to take a heavy star and think about how long will the fuel last if we fuse hydrogen into helium, let's say for the sake of argument it lasts for many, many millions of years. Once the hydrogen has fused into helium, remember we've got the same number of kilograms of helium, and if the star compresses, it'll become hot enough to start fusing helium into the heavier elements, but it is less efficient. So although we've got the same number of kilograms, roughly speaking, of fuel, it's not going to last as long. If we want to keep that star in balance, we're going to have to fuse helium into carbon a lot faster in order to keep the gravity radiation balance. So the phase of fusing helium into carbon doesn't last as long as the phase of fusing hydrogen into helium. And similarly, the same number of kilograms of carbon, when eventually it comes round to the star compressing until it's hot enough to start fusing carbon into heavier elements, that phase won't last as long, because the same number of kilograms have to be used up much more quickly to balance the forces of gravity. And so that phase might only last a few thousand years. And burning or fusing neon into oxygen, that might only last 10 years. The star might have lived for many millions of years, but each cycle doesn't last the same length of time. It's getting faster and faster and faster, like an avalanche. And when we start burning oxygen to make silicon, that might only last 5 years with the same amount of fuel. And most scary of all, when it comes to burning up to the point where we generate iron, that last phase might only last days. And then the question is, where do we go from there? Here's the periodic table, which I'm sure you're all familiar with Mendeleev in the middle there. Let's just dim some of that out so as not to get too distracted. So we've got hydrogen in the top left and helium in the top right. And we've got various other elements which I'm not going to dwell on too much. But the point is that we can understand some of the key points and we can fill in the gaps from hydrogen to iron. But of course, when we reach iron, we're only at element, 26 out of all the elements that we know exist on Earth, up to 90 or so, and we can generate a few beyond 90, but we've got 92 naturally occurring elements. But this idea of stars being fusion factories to generate the elements only works for, 1/3 of the periodic table, or maybe even 1/4 of the periodic table. So how are we going to explain the existence of copper or silver or gold? Is another one that's often taken as being a very heavy element, but it's a long way heavier than iron, and we can't explain that by stars fusing at their cores, because we know that that takes energy. It doesn't provide a way for stars to generate energy. So there must be something else going on to generate heavy elements. And of course, that is the big question. Why does gold exist? Not just gold, it's just a convenient question. If we know that hydrogen can make helium and then the heavier elements up to iron, and we know that iron does not release energy because iron represents the peak of that particular curve, but needs an input of energy, if we want to explain the heavy elements, we have to look beyond how do stars live, and we have to ask the question, how do stars die? So let's have a think about that. For a medium mass star, and by medium mass I mean something perhaps similar to the mass of our Sun, gravity may not be strong enough to hold on to the outer layers. When the helium starts to burn, when helium starts to fuse to generate heavier elements, for instance carbon, it might be that gravity simply isn't strong enough, there's not enough mass there for gravity to hold on to the outer layers of the star. and the star expands to become a red giant. This is the phase that I showed right at the start in the first slide of this particular talk. That's why stars tend to bloat and produce the red giant phase. Relatively low density, but gravity is finding it difficult to hang on to the outer part of the star. And these giants are in this part of the diagram. Remember, we've got the sun there, so when the sun comes to the end of its life, it's going to move in this direction. Its surface temperature is going to go down slightly, and it's going to become more luminous. So it's lower temperature, but because it's a much larger surface area, it becomes more luminous. So red giants tend to be relatively bright. The helium being fused in the core can become unstable, and the outer layers might be given enough energy to be blown off completely from the star. In other words, gravity completely loses its battle to try and keep the outer part of the star attached to the rest of the star. And if the outer atmosphere of the star is blown away completely, it can form what we call a planetary nebula. Nothing to do with planets at all. They were simply viewed in the early days of astronomy as spherical objects that looked a little bit like planets. And if the outer atmosphere is blown away into a planetary nebula, the core of the star that's left is a white dwarf. And a white dwarf are these stars down here on the bottom left. They have got relatively high temperatures because they were a core of a star. And remember, the core of a star is much higher temperature than its surface. So that's why white dwarfs are quite hot and tend to be over on the left-hand side of the diagram. But they're not particularly luminous simply because they're quite small. They're about the size of the Earth or so. And here we see a picture of a planetary nebula, and you can perhaps understand why viewing planetary nebula, especially in a telescope that doesn't have a particularly good resolution perhaps, you can see in the early days of astronomy why people looking at these star atmospheres that have been blown out into a huge shell of gas, why they were labelled planetary nebula, because they superficially give the appearance of a spherical planet. Well, some of them do. In fact, a minority show a nice spherical structure. Given that most stars are actually rotating, when the atmosphere gets blown off, you can get very complex structures produced. And people study planetary nebula to actually get a better idea of star dynamics, because that tells you something about how stars spin. Whether or not this is a single star, whether it's been influenced by a neighbouring star, people are looking at these structures trying to understand the dynamics of how these are produced. And some of these planetary nebulas, although the star atmosphere might be relatively large compared to the star, they're still not particularly large on a cosmic scale, but some of them are actually close enough to Earth. This particular image is taken with the Hubble Space Telescope, but this particular planetary nebula is actually close enough to Earth that if you look in the bottom right inset there, that's a picture of the planetary nebula taken with a telephoto lens. Not a telescope, just a camera with a telephoto lens. So that tells you that these things are, in that sense, large. If the particular planetary nebula is not too far away, this particular planetary nebula is a fraction of the size of the full moon. It's not particularly bright, which is why you don't tend to notice these things, but if you know where to look, you can see this with a pair of binoculars, or you can photograph it with a telephoto lens. If we have a high mass star, remember I've just been describing what we might have with a medium mass star like our sun, so that's what our sun is probably going to do, swell to a red giant, probably lose its outer atmosphere and end up as a white dwarf. But if the star has much stronger gravity, if it starts out as a very high mass star, let's say for the sake of argument 10 times the mass of our sun, then the gravity can hold on to the outer part of the star through the process of fusing helium into carbon and through the later stages as well. And so what you might end up with is a star that looks a little bit like an onion. There might be inside the star hydrogen that's been converted into helium, and helium into carbon, and carbon into neon, and neon. And this might continue all the way down to the hottest part at the core where silicon is being converted into iron. If there's enough gravity, then all of these processes can continue in sequence, and the gravity is strong enough to hold the star together whilst these various cycles are being taken through. But, as we've said, at some point it gets to the point where there's no fuel left, or little fuel left, that can support the enormous forces of gravity that are trying to crush this star. When silicon has burnt into or fused into iron, we can't go any further beyond iron. And what happens? The radiation forces no longer balance gravity. We get a catastrophic collapse. The collapse can crush the core down to the size of, not the size of the Earth, but down to the size of just a few kilometers. And a shockwave rebounds from the core and effectively ejects everything else in the star out into interstellar space. And what we end up with is a supernova. Here's a supernova that was visible from Earth in about 1054. It was recorded in Chinese records. What we see when we look at that part of the sky now is a supernova remnant. The star is, well, it might be in there somewhere, but I can't even see which one it is. But most of the star itself, most of the outer parts of the star have been completely blown away and are now seeding interstellar space. And what's left is a tiny star at the core. The amount of energy, well, we can roughly speaking work out the energy. Very crudely, we can simply say, well, if this is a star, how much energy is required to take each piece of that star and separate them to infinity. That's a crude way of working it out, but it gives you a ballpark figure of how much energy must be in a supernova in order to blow a star apart. The answer is in the region of 10 to the power 44 joules, which is a difficult number to get your head around. So one way of thinking about it is imagine all of the energy output from the sun. Our sun is not a massive star that's going to go supernova, but just think of the total energy output of the sun. Not the tiny amount that Earth receives, which of course is just a tiny solid angle. Think about the total amount of energy that the sun has outputted for each and every second of its 4.5 billion year life and what it's going to do in the next 5.5 billion years. So if you imagine the energy output of the sun integrated for the entire 10 billion years of its life, and imagine all of that energy released in just a few seconds. That effectively is a supernova. That number there, 10 to the 44 joules, is roughly speaking the energy output of the sun for its entire life. And in a supernova, that energy is released in little more than an instant. The word explosion is not really the correct word, and it obviously just isn't really big enough as a word to describe the immensity of a supernova. And it's during the melee, it's during the supernova that nuclei fuse together to create elements heavier than iron. In other words, it's the supernova that puts the energy into the fusion process that allows iron to fuse into heavier elements. In principle, all the elements up to and probably beyond the periodic table as we understand it. Almost certainly very heavy elements are made and then decay into slightly more lightweight elements. So all of the elements that were generated during the star's life and are also generated in its death, they will get ejected into interstellar space. So a small amount will be left in the core, whatever's left behind, but most of the star, certainly everything that's been generated up till iron, and certainly elements heavier than iron during the supernova itself, all of these will be ejected in the sort of remnant that we see in that image. So the heavy metals that we're talking about found on Earth were probably made in a supernova. So that means the sun is probably more than simply second generation. If these elements are around on Earth, that means that the solar system must have already had heavy elements in it, even before the sun started doing its stuff and started fusing hydrogen into helium. Which means probably the sun is not second generation, it's probably third or fourth or fifth or sixth generation. Stars were born, stars died, seeded the surrounding material with slightly heavier elements, and then they collapsed to make stars, which were then born and lived and died, and they exploded, and again some of those heavy elements seeded the molecular clouds which were floating around the galaxy. This process has gone on, and this recycling of elements has happened a few times to enrich the hydrogen clouds with more and more heavy elements, such that we can end up with a solar system in which we see lots of elements in the Earth today. And in a sense, our atoms are not ours. The atoms in your body are not yours. You're just custodians for the time being. The atoms in your body were made in a star, probably died in a supernova, redistributed the atoms throughout space, probably more than once. You're going to use the atoms for a while, and in a few billion years those atoms will go back into the hydrogen clouds in our galaxy. That's just a sobering reminder that you're just borrowing the atoms for the time being. This is an indication of where most of the elements might have come from. So we know that hydrogen and indeed helium, but I'm not going to talk about that, were made in the Big Bang. So I've been talking about hydrogen being converted into helium in stars. Well, that's true, but actually quite a bit of helium was made in the Big Bang in the first place. But in terms of the heavier elements, we can see that stars are responsible for the green squares, and some of those large stars will produce some of the heavier elements, and in particular the supernova are thought to produce some of these heavy elements all the way up to plutonium. They're defined here as man-made beyond plutonium, but I'm fairly sure some of those will be made temporarily in supernova explosions before decaying back to some of the lighter elements. This picture isn't necessarily correct, because more recently it's been thought that supernova are not the only ways of making some of the heavier elements, because of something I'll say in just a second. Once a supernova has done its thing and basically ripped apart the outer regions of the star and produced a supernova remnant, the star's core has been crushed, so what is actually left behind? Not an object the size of a white dwarf, which is about the size of the Earth. What's left behind after a supernova is a star that might only be a few kilometers in diameter, a neutron star. And a neutron star will have the density, roughly speaking, of a nucleus. In other words, it no longer is made of atoms. We have gone beyond that and crushed things down such that the idea of a nucleus with electrons going around it, that's been completely thrown out of the window. Now we have effectively just a soup of neutrons with enormous magnetic fields spinning at very high rates. It's interesting to note that people think a neutron star is not necessarily uniform across its entire volume. It might well be that a neutron star has got something akin to a liquid interior and a solid crust. That would be a very interesting thing to do some geology on, I guess, but I'm not going to go into that. That again is probably a whole talk in itself, the nature and the physics of neutron stars. But it is thought that these very interesting objects might ultimately collide with each other, and there is evidence from the latest gravitational wave detectors that neutron stars collide with each other, and that is such a violent event that it is thought that this in itself might be the origin of some of the heavy elements, not necessarily born in a supernova explosion, but perhaps neutron stars are actually responsible for generating some of the heaviest elements. That's still rather speculative at the moment, but it's an interesting idea. Now we know neutron stars have only got a size of a few kilometers or so, and that's the limit by taking all of the mass in the core of the star and crushing it until all the nuclei, effectively all the neutrons, are now touching each other. Okay, in quantum mechanics we can't really talk about objects actually touching, but effectively the protons have turned into neutrons and the neutrons are all crushed together into one big sphere, one big bag of neutrons. And they really don't want to get pushed together any more closely than that. We don't want, or neutrons do not want to overlap with other neutrons. But if the star has enough mass, then gravity wins and the neutrons are effectively forced together despite their objections, and nothing can stop the collapse continuing. Nothing we know of can prevent gravity just making the object smaller and smaller and smaller. Not kilometre sized, but smaller. Not tens of kilometres, but smaller than kilometres, perhaps even nothing as far as we know. The result is, of course, the stuff of science fiction, black holes. So we don't know how large a black hole is. As soon as something the mass of our sun gets compressed to a size smaller than a few kilometres, then the escape velocity goes faster than the speed of light, and then nothing can escape from this region. And it's thought that if a black hole forms close to another star, then a black hole can start feeding off a neighbouring star. The star's material doesn't simply go straight down the plug hole. It basically, just because of the conservation of angular momentum, the matter that's trying to fall into the black hole ends up as a sort of accretion disk, which itself gets very hot. So there can be a great deal of radiation, not from the black hole itself, but from the matter that's trying to fall into the black hole in the region just around the black hole, the so-called accretion disk. But as far as we can tell, that has no particular role to play in the formation of the elements. So let me just remind you in words first that we looked at birth, life and death. We looked at how clouds collapse to form stars, how everything in a star is the ABC, is the balance and the acceleration of fusion and the compression of stars producing more heat. And because iron is a stable nucleus, we can understand the generation of elements up to iron, and beyond iron we have to invoke some other mechanism, such as supernova explosion of a massive star, or perhaps collision of neutron stars, to explain the existence of all the elements above iron. Let me just summarise in a graphical form what I've just said. If we start with a shed load of hydrogen, it could be pure hydrogen, or it could be hydrogen that has been enriched partially with a few heavier elements. That cloud, if you leave it alone for long enough, might form a small star which might live its life quite happily for billions of years, and might form a solar system in which planets exist and geologists evolve to start banging rocks together. At the end of a small star's life, it might expand up into a red giant, and because gravity has difficulty holding on to the outer atmosphere, that can often be released as a planetary nebula, so that the outer atmosphere effectively recedes the environment. It goes back into interstellar space. What's left in the core is the core of the star is hot. It's a white dwarf. It's hot, but it's not actually undergoing fusion anymore, so the star simply starts out white hot, and if you wait long enough, it will get dimmer and dimmer and dimmer and colder and colder. So eventually our star will simply fade away, if that's the ultimate fate of our sun. The cloud might form a small star, but it might also form a larger star. That's sort of luck of the mill in terms of how the star collapses. If it forms a large star, then the star might go through various cycles of fusion, of coming out of balance, compressing, heating up, fusing the next elements in the chain, as it were. And if the gravity is strong enough, this cycle will continue all the way to iron, where the star has no choice. It cannot go beyond iron. So at that point, the star collapses, and the rebound sends most of the matter of the star off into interstellar space in a rather more explosive version of the planetary nebula. And what's left in the core might end up as a neutron star, or perhaps, if the star was massive enough, might end up as a black hole. But notice that in both cases, small stars or large stars, a fair amount of the matter that was generated is recycled. As a planetary nebula or as a supernova, a lot of those heavier elements gets recycled back into the molecular cloud, and it enriches the hydrogen cloud so that the next generation of stars are born with just a few extra of those heavy elements. And if you go round that cycle a few times, you will end up with the sun and an Earth that is full of not just hydrogen, helium and a few elements, but elements filling the periodic table. Thank you for listening.